Okay, so hello guys. Now we're going to see about laser, the fifth unit of engineering physics. It is one of the easiest chapters, and you can score well in this. So yeah, let's dive into it. So let's see what are lasers actually are. I mean, laser is not a single word. It is an abbreviation of light amplification using stimulated emission of radiation. So this pretty much explains what laser is. Okay, so we are amplifying the light using stimulated emission of radiation. Okay, so first let's get to know about the characteristics of a laser. Okay, uh first absorption and emission of radiation, Einstein coefficients, population inversion. These are very important characteristic of a laser because first this population inversion is what is helpful to create the lasing action. Okay, and pumping, achieving population inversion. So these are all the topics that we are going to see in the upcoming slides. Okay, uh, we have different types of laser like optical laser and a semiconductor laser, gas laser, and stuffs like that. Okay, so first let's see what a laser is. A laser is a device that emits a narrow intense beam of light through the process of stimulated emission. Okay, we have all, obviously we all have seen what how a laser is. I mean, how it works. Like if we turn on a laser, it goes in a straight line, and no different colors are expected out of it. Just a single wavelength of light is emitted out of that device, right? So that is some of the characters of laser. Okay, lasers are okay. What's inside a laser is what makes it interesting. Okay, these are made up of a gain medium, a system mirror, and a power source. These three pretty much is makes the laser work out. Okay, uh when an electric current or energy source is applied to the gain medium, it becomes an excited and emits photon. Okay, we'll elaborately see what this line is about in the upcoming slides. Okay, I mean, this pretty much sums up how the photons are generated in a laser. Okay, I mean, let's take this line, but the thing is, this will be elaborated further in the upcoming slides. Like these photons bounce back and forth the mirrors, and yeah, I'll explain it in a detailed manner in the upcoming slides. Okay. Okay. Now let's see the properties of laser. Okay. Directionality. Laser is highly directional. There are mainly five uh, properties. Okay. First one is directionality. When we shoot out a laser, we have used the point lasers, right? It is directional because it doesn't scatter like a tube light or a torch light. It goes in a straight way, like in a very straight manner, right? If we point it from a distance to some like 20 meters or 30 meters to another object, it precisely points out, right? They are using lasers in guns and stuff like that to point, right? So it is highly directional. Okay, no distraction, no the divergence, the angle of divergence is very much less in lasers. Okay, monochromatic. And if we see just only one type of color, either red, green, blue type of laser, for example, okay, this just these colors, i mean those those colors don't deviate from that wavelength. Okay, so it is highly monochromatic. The wavelength will be very much fixed onto a spectrum. Okay, not like white light because it has multiple wavelengths, right? But a laser only has a dedicated small uh, spectrum of wavelength. Okay, coherence. We all have studied about the coherence, right? The, how can we say that constructive interference, destructive interference, and what is high coherence and low coherence and all. So in our 12th standard, I guess, yeah. So Coherence, I mean, the laser lights are actually very coherent, meaning that each light waves are in phase with each other. I mean, they don't distract each other; they constrict each other. Okay, so that's why those are highly coherent. That is because of the property of I mean, the lasing action. Okay, and then intensity, because the same amount of photons are carried in a single how can I say, single point. Okay, so the number of photons in a single point is so much high that it will be so intense. Okay, and polarization, laser light is typically highly polarized because electric field of this light is specifically pointed in a how can we say, specifically pointed in a specific direction. Okay, so that's why we call this laser polarized one, highly polarized one, because it is aligned in a certain direction. Okay, so okay, uh, this is just about the directionality, like how if in ordinary light the divergence angle is very much greater, but in laser we, I mean, it is very straight. Okay, and monochromaticity, the deviation of the frequency is almost zero, not exactly zero, but almost zero, which makes the laser light very monochromatic. Okay, okay. This slide is about how it is highly directional. Okay, the distance and the angle of divergence. I mean, the radius of the circle on those 2 points are how can we say? It's okay. The divergence is the difference between, I mean, the rate of change of the radius of that uh, point here. Okay, between the distance. Okay, the rate of change of the radius with respect to the distance between those 2 points. So that is the angle of divergence here, and it will be very much lesser, like 0.0001 kind magnitude. So it will be highly directional. Okay, so this again says about the directionality. Okay, that means the due to the lasing action, the photons are emitted, right? Those photons which are how can we say, uh, which are in a polarized manner. Uh, the polarized photons can only be emitted out of that cavity. Okay, so that's why in a specific way those photons are emitted. Okay, so in that direction only it travels. So therefore, it is highly directional, is what this slide is about. Okay, and it has some numericals about how to find the angle of divergence, but it is not that important for the exams. And as I said, it is highly monochromatic. As you can see, the deviation of the frequency is very much less here. As you can see the graph here, the frequency difference is very much less. Okay, so therefore, the monochromaticity is higher. I mean, yeah, just only one type of color is emitted out of this laser. Okay, so and again, this formula is about the uh, deviation and the frequency, and it will also be very much lesser. Okay, yeah, as I have said, monochromaticity refers to a pure spectral of color of a single wavelength. Okay, and as I have said, coherence and intensity is about coherence is no distraction happens. That is, it is highly coherent, so that it constructs each other. And intensity is that high, as I have said, more number of photons are I mean directed into a single point, more not a single area. It's like a single point. Okay, so it is highly intense, like one. 1 watt is converted to some 10.9. I mean, I don't understand. I mean, I didn't get what. I mean, wow. I mean, not what. It. Uh, Never mind. Okay. Let's see about what a coherent source is. Coherent waves. Okay. Let's see about the coherent waves. I mean, lights are actually. I mean, it has dual nature. I mean, mostly it is wave, right? I mean, not mostly, it has dual nature, but the thing is, if it acts as a wave, it can either construct or destruct with other waves, right? So, i- if we take laser, it construct each other due to the property of the resonant cavity. That I'll explain later because in the resonant cavity, all the lights are I mean, the emitting lights which have survived the resonant cavity will will be in the same. I mean, will be in the same phase. Okay, so that's why it constructs and gives us a highly coherent laser wave. Okay, okay. So basically, that is what coherence is, and the temporal coherence and the I guess spatial coherence is not so important as far as we consider in the exams. Okay, I'm just explaining what I mean those properties and the things that we require to write in the exams. Okay, and yeah, this tells I mean this formula tells about the brightness of it of a laser. Okay. So finally, we have a summary of those things that we have seen in the previous pages. That is, laser is a device that generates highly intense, monochromatic, coherent, and directional beam of electromagnetic radiation. So these are the main properties which defines the laser. Okay, through the process of repeated amplification of stimulated emission. Okay, uh, I mean, when we learn about the resonant cavity, we'll see about how what the repeated amplification and the electromagnetic radiation are. Okay. The main characters are it is highly intense, highly monochromatic, highly directional, and highly coherent. So these are the main four properties. Okay. And the degree, I mean, these formulas are not so much of important, but yeah, angle of divergence is A2 minus A1 divided by 2 D2 minus D1. So basically, it's the difference in the how can I say? It is the difference in the distance divided by the difference in the radius of those 2 points. Okay. Okay, now here is an interesting question. Okay, is brightness of laser source equal to a ordinary light source given equal number of photons? So obviously, no. Okay, because in ordinary source, the light is scattered. It is not directional. Okay, so the number of photons per area, I mean the concentration, that is the intensity, will be lesser. Okay, but here in a laser, the if we given the same number of photons, the intensity will be higher because it is a point source, right? It is only a single point which has the same amount of photons as of ordinary light which was scattered all along the area. So obviously no. So this is the basic answer. Okay. Okay. It is the same summary. Okay. Now spatial coherence is something uh of two spatially separated points traverse to the direction of propagation of wave at the same interest I mean instant of time. Okay, how can I say, if it's like taking 2 points and at two different points of space, and at the same instant of time we are taking the I mean we are comparing those waves, I mean waves. Okay, and in temp temporal coherence we are taking with respect to time. In spatial coherence, we are comparing two different waves with respect to the space, and in temporal coherence, we are comparing two waves with respect to time. Okay, time duration for which the radiation emitted from us. I mean, these are not that much important, I guess. Yeah. So now we are coming to a topic of Einstein's coefficient. Okay. So basically, how photons are generated from an atom. When a electron from a higher level comes to lower level, right? So that's when uh, the photons are generated. So as you can see in absorption, energy source, it can be light or heat or some energy. Okay, when it is absorbed, it goes from ground state to an excited state from E1 to E2. Let's say E2 is higher energy. So this E2 has that energy of H mu. So E is equal to, I mean, the energy is H mu, H into frequency. Okay. So this is what absorption is. So energy is equal to H mu. That is the difference between E2 and E1, right? So the energy required is from E1 to E2 is E2 minus E1, right? So that is the energy. So H mu is equal to E2 minus E1. So here RAB is Einstein equation rate of absorption. Okay. Here we are assuming okay rate of absorption in the Einstein equation is RAB. Okay. So B12 is absorption coefficient. B12. I mean it's from 1 to 2. Okay. So we are equating the energy in absorption. Okay, not emission. In absorption, we are saying it is RAB is equal to, I mean, the rate of absorption is equal to B12, the absorption coefficient that we are defining right now, and into N1. N1 is the number of atoms in the ground state that is in the E1, and into U mu. Okay, so U mu is the density of the radiation that is coming out. I mean, the radiation coming from outside, right? This H mu energy. So that is multiplied here. So the rate of absorption, the Einstein equation rate of absorption is P12, the coefficient into the number of electrons into the density of radiation. Okay. Okay. Now we have seen about the absorption. Then let's see about the emission. So emission is what creates the light. It gives out the photons, right? So emission is of two types: spontaneous emission and stimulated emission. So spontaneous emission is takes place without any external energy. Okay, but stimulated emission is not like that. With external energy, it takes place. So in spontaneous, spontaneous emission is used in LEDs. Stimulated is used in lasers. So let's see about the spontaneous thing. Okay, so its lifetime is 10 to the power minus 8 seconds, so it is very very much lesser to sustain a lasing action. Okay, so that's why we use stimulated air emission. Okay, here RSP, that is rate of spontaneous emission, is A21, from 2 to 1, from E2 to E1, right? So that is the Einstein coefficient for emission, A21 into number N2. N2 is number of atoms in E2. Okay. In similar way, in stimulated emission, it is RST, the rate of stimulated emission is B21, the Einstein coefficient, into N2, number of atoms in E2, and in U mu, because we are using an external energy to make it happen. Okay, so we are multiplying the U mu, the radiation density in stimulated emission. Okay, so now we are going to relate the Einstein's coefficient with each other. Okay, so in Boltzmann distribution law, the number of electrons is equal to n naught into e power minus energy divided by k into temperature. Okay, so this is the formula. The number of electrons is equal to n naught into e power minus energy in specific level divided by K and absolute temperature. The K here is Boltzmann constant. Okay. So first, let's take for the energy level one, that is N1 is equal to N naught into E to the power minus E1 divided by KT. And similarly, it is E2 instead of E1 in the place. So when we divide it, we N2 minus divided by N1 will give out an answer of E to the power minus E2 minus E1. So this is basically the energy gap between the both levels, right? Guys, 1 minute, please.